Okay, good afternoon, ladies and gentlemen. Before we start our panel discussion this afternoon, it's my immense pleasure to introduce our very special guest speaker who will open the session. Dr. Takashi Yasuda is the Director General of the National Measurement Institute of Japan, but also a member of the International Committee of Weights and Measures. So he has reached two pinnacles that any metrologist aspires to. So we're very lucky to have him here, and Dr. Yasuda, I'd like you to make your presentation, please. Thank you.
Can I have a controller for slideshow? Distinguished guests and researchers and ladies and gentlemen, good afternoon. It is my great pleasure and honor to address this conference on behalf of the international metrology community. My name is Takashi Usuda, Director of the National Metrology Institute of Japan, and the Secretary of the Committee for International Weights and Measures, namely CIPM. This is the first time that the International Metrology Organization has had the opportunity to participate in this SnT. If you remember the opening speech of the CTBTO Executive Secretary, Dr. Floyd, yesterday, we can recall how important measurement reliability is. Today, I would like to present the history of the metric system, how measurement equivalence is maintained in the modern context, and also the recent fruitful cooperation between the CTBTO and the metrology community. Okay, could you show the slide on the screen? Yes. I would like to start by explaining the origin of the modern measurement unit and system known as the metric system. The metric system was first introduced after the French Revolution to allow fair trade by weight and length. The original definition of quantities are the meter is 1/10 millionth of the arc of the meridian between the North Pole and the equator. The kilogram is the mass of 1 decicubic meters of water at its temperature of maximum density. The metric system was originally a French national system. Then the demand for more accurate measurements based on a common standard increased in the international community. For example, in the military field, to express the range of artillery, or in politics to determine borders by land surveying. And the French government actively promoted the metric system using its influential position. Over time, the superiority of the system became clear as more and more countries recognized the benefits of standardized measurements. In 1875, international agreement cemented its state as the Metro Convention, signed by 17 nations. And today, 64 nations are signatories to the convention. The realization of the units at that time were the metal objects, a rod for the metal, called the international prototype of the metal, and a cylindrical mass for the kilogram, called the international prototype of the kilogram. The dissemination of the standard was achieved by the distribution of exact copies of the international prototypes of the metal and the kilogram to the member states. National metrology institutes in short NMI, were set up in each country to maintain the copies and to calibrate the equipment of national customers. The International Bureau of Weights and Measures, BIPM in short in French abbreviation, in Paris, maintains the international prototypes and periodically calibrates the member countries' copies. This is the original concept and mechanism for ensuring the uniformity of measurements under the Metal Convention. Since its start in 1875, scientific advances and social demand have led to the inclusion of additional units such as the ampere, the Kelvin, the candela, and more. This evolution transformed the system into the International System of Units, SI, making it more comprehensive and universally applicable. As scientific discoveries progressed, certain unit standards moved from being based on physical artifacts, such as a metal rod, to being defined by fundamental physical phenomena. For example, the metal is defined by the speed of light, as Dr. Freud introduced in his opening remarks yesterday. This elegant shift has ensured greater accuracy and reliability of measurement in line with the ever-expanding frontiers of scientific understanding. The current international system of units, the SI, defines its 7 base units based on fundamental physical constants or atomic properties. The kilogram is based on the Planck constant, the ampere by the elementary charge, the Kelvin, thermophysical temperature, by Boltzmann's constant, the mole by the Avogadro constant, and the metal by the speed of light, the candela, unit of luminous intensity, by a source emitting monochromatic radiation of a certain frequency, and the second, time, by the frequency of radiation from the cesium atom. National Metrology Institutes utilize these definitions and employ advanced quantum technologies to realize each quantity accurately. As well as the 7 base units, standards for derived quantities have been established by National Metrology Institutes, NMIs. These NMIs are able to provide independent calibration services for derived quantities such as vibration, meter per square second, or sound pressure, or underwater acoustics in Pascal. These photos show the vibration standard developed by the German, Japanese, and US laboratories. Is this a happy ending? No need to ensure consistency and equivalence between established standards. However, in reality, it is not so simple. Primary standard of each NMI may vary within its uncertainty level, even base unit quantities. Hence, explicit mechanism for providing equivalency of measurement calibration certifications issued by NMIs has been requested. Based on the fact and the demand at the CGPM in 1999, member states signed a mutual recognition arrangement drawn up by the CIPM. Hereafter, CIPM MRA for national measurement standards and for calibration and measurement. The essential aim of the CIPM MRA is to confirm the degree of equivalence of calibration and measurement capabilities, CMCs, maintained by each NMI. Going back to the structure of the Metro Convention, there are several decision-making and executive bodies under the convention. The General Conference, what I mentioned in the previous slide, CGPM for short, is the highest authority for discussing or decision-making body for international metrology. It normally meets every 4 years. The draft decision to the CGPM is proposed by the CIPM, which has 18 members. I'm one of the members. In this means, I'm a guardian to protect the metric system. Under the CIPM, there are several consultative committees, technical committees, namely CCs in short, which discusses specific technical issues. And the International Bureau of Weight and Measures, BIPM, acts as the secretariat for the CIPM and the CGPM, providing administrative and technical support. It also plays a crucial role in ensuring consistency and equivalence between the established measurement standards of each member NMI. Based on the technical and fair trade requirements recognized by the CCs, the CIPM proposed to the CGPM to establish the mechanism to ensure the equivalence of measurement standards as a regular function under the Metro Convention. This is CIPM MRA. Here I introduce the consultative committees, or CCs, of the CIPM. The CCs are composed of scientists from National Metrology Institutes, NMIs, and cover scientific areas of metrology, including length, time, electricity, and others. Their main role is to provide technical expertise, guidance, and recommendations in their respective fields. Among them, you will see the cooperation between the CTBTO and the CCAUB, the Consultative Committee on Acoustics, Ultrasound, Vibration, in later this presentation. The CIPM MRA, Mutual Recognition Arrangement, follows a 3-step process to ensure the equivalence and the comparability of calibration measurement capabilities, CMCs, among NMIs. Firstly, the respective consultative committees identify mandatory comparisons for each CMC. Next, the comparisons are carried out by a pilot laboratory, and participating NMIs examine the reference values and uncertainties. Lastly, the CMCs of each NMI are reviewed based on the comparison results and other supporting evidence under the supervision of the CCs. Accepted CMCs are published on the Key Comparison Database, KCDB in short, website, establishing a globally accessible resource for validated measurement capabilities across NMIs. This process fosters trust, confidence, and harmonization in measurement standards internationally. The current quality infrastructure for measurement is based on a combination of key principles, horizontal agreements such as the CIPM MRA and the International Laboratory Accreditation Corporation ILAC MRA. It ensures the recognition of calibration and test results between accredited laboratories worldwide. Document standards established by organizations such as ISO and IEC provide guidelines for measurement processes, ensuring uniformity and consistency. Accreditation by the International Accreditation Forum, IAF, signifies that laboratories meet specific criteria and demonstrate competence. Together, these principles provide a robust framework that promotes harmonization, trust, and confidence in measurement results across countries and sectors. I would like to draw your attention to the fact that UCAN or CTBTO can use a similar structure to ensure the measurement equivalence of each of your IMS. Your calibration source should be traceable to the national metrology standard, whose capability is verified under the CIPM MRA. The measurement procedure and key specifications of each IMS should be standardized. The operation of the IMS, such as the calibration cycle and staff training, should be assessed by the authorities. By the way, how the intercomparisons are achieved. As mentioned in the previous slide, respective CC consultative committee defined the measurement subject and fixed the participating NMIs from the member countries. In this case, from Asia, Japan, China, South Africa, and Europe, from Germany, and the US, NIST, the corresponding NMIs in each member state. The participating NMI measures the common object, so-called traveling standard, under the common measurement condition. Those participating NMIs play a role as link laboratory for regional comparison afterwards. In this case, just a balance, but in reality, we will provide a seismometer for vibration, or microphone for acoustics, or underwater microphone for underwater acoustics, so on. Then the link laboratories in each region organizes each regional comparison in which the additional NMIs will participate in the respective comparison. After the regional comparisons, degree of equivalence of the participants, all participants' measurement result is analyzed. This is one of the achievements of the global compatibility of the measurement in acceleration or vibration measurement in the frequency range from 40 Hz to 5 kHz. The central red circle represents the participants to the first global level comparison done from year 2000 to 2001. Then the regional comparisons have followed for other participants in Asian, American, and European regional organizations. This graph shows the equivalence of each NMI obtained by the comparison. The colored dot represents each participant's result at 40 Hz frequency of vibration. And the bar represents their uncertainty. I won't go into the details, but you can easily imagine that this is a very time-consuming process. It takes a year or more to complete a single comparison cycle. When the CIPM MRA started, we NMIs had different measurement methods and different conditions. So we had to discuss a lot to harmonize the conditions and procedures. During the measurement, of course, the stability of the measurement object, in our case, seismometer or microphone, the traveling standard should be carefully monitored to assess its stability. The statistics method for evaluating the measurement results should also be standardized. Similar activities in infrasound, underwater acoustics, and ionizing radiation measurement area also progressing by the respective CCs and NMIs. More than 20 years since the start of the CIPM MRA, we have accumulated a lot of experiences, such as established agreed measurement conditions and procedures. We call it protocol. Agreed evaluation of degree of equivalence by statistics method. Evaluate the calibration object characteristics, such as stability, aging, etc. The signatories to CIPM-MRA has been increased, including international organizations such as IAEA, European Space Agency, ESA, European Commission Joint Research Center, JRC, and WMO. Number of results of CMCs and comparisons, numerous number of the data are published in a key comparison database, namely KCDB. Anyone can access to the data from the website described the address on the top of this slide. Here I talk about the collaboration between CTBTO and CIPM. Since year 2016, relevant researchers belonging to relevant CCs, CCAB for acoustics, ultrasound, and vibration, and CCRI for ionizing radiation have been communicated with CTBT staffs. Then, June 2021, a practical arrangement is signed between the CIPM and the CTBTO on collaboration on the metrological traceability of measurement of infrasound, seismic vibration, and radioactivity. Now, CCAB and CCRI are official liaisons of CTBTO. Under this arrangement, the CCAB and CCRI assist the CTBTO in its role to provide the state signatories with data and products on the highest quality standard, including reaching compatibility and adherence to the International System of Unit, DSI. As I mentioned earlier, conventional vibration comparisons have been made down to the level of a few tenths of hertz. I can say down to 40 hertz, since the main industrial requirements for vibration measurement are in the range of a few tenths of hertz to a few kilohertz. Recognizing the need for low vibration measurement reliability in the IMS seismic monitoring area, some advanced NMIs established the national measurement standards for very low frequency down to 0.01 hertz. Relevant NMIs also planned comparisons for these early topics. Therefore, I expect that these activities in the metrology community will be disseminated to the meteorology community to ensure the measurement capability, including IMS. And here are the conclusions of my talk. Under the CIPM-MRA, equivalency of national measurement standards are confirmed. Established framework under the CIPM-MRA can be introduced to any other technical fields to ensure the measurement reliability. More advanced measurement technologies are developed at NMIs, recognizing the need from IMS. And finally, geologists, seismologists, and meteorologists, you should collaborate with us, meteorologists. Thank you very much for your attention.
Thank you very much, Dr. Asuda. So just one quick question from me before we turn to the audience. These calibration and measurement capabilities, there's obviously a large amount of investment to generate those numbers. There's a lot of effort goes into prepare those numbers through the comparisons and so on, as you described. Are those, first of all, how does a new capability enter onto the database, and can the science and technology community access that information?
Yeah, based on the current structure of the CIPM-MRA, the CC programs the new entries or new comparisons. But the CC recognizes these or surveying the needs from the scientific communities or industrial demand. So I think especially among between the CTBTO and CIPM, we can expand the area of the CMCs. And those of the advanced NMIs, like in Germany or France or UK or US, they are also expanding their measurement capabilities, which has not been confirmed yet under the CIPM MRA, but it will be confirmed in the future.
Thank you. Does anyone else have a question for Dr. Usuda? Please, there's a microphone in the center. I think there's some at the sides of the room, so if you'd like to ask a question, please do step up. As the moderator of the panel before me mentioned, that if you're thinking of a question, it's likely that half the room are thinking of the same question, so please feel free to step up. No, it doesn't seem like there's any further questions. Does any of the panel have questions for Dr. Usuda before we finish? Okay, in which case, thank you once again very much for that presentation. So I'd like to now start the panel discussion on the operation of the IMS in the framework of the International System of Units. First of all, my thanks once again to Dr. Usuda for so clearly describing this vital framework and the mechanisms that underpin nearly all measurement activity, regardless of the technological field. But it's maintained in the background and it's largely invisible to most of us. And in fact, this is the very same framework that Dr. Floyd referred to so eloquently yesterday in his opening address. So my thanks to both Dr. Floyd and to Dr. Usuda for providing the perfect introduction to our topic today, which is seismoacoustic measurements and the metrology considerations necessary to bring these in line with the International System of Units. So the system we know is the SI, or the metric system. And we'll look at also the benefits of doing so. So we'll also perhaps touch on some of the strategic goals for future development for realizing these benefits in a complete way. So I'll be the moderator. I'm very pleased to be asked to moderate this panel. It's a very big privilege for me. My name is Richard Barham, and I am a specialist in acoustics. I've spent my whole career in research in the acoustics world. And we have a rather unique gathering of expertise today, bringing together the fields of geophysics and metrology, with a specific focus on seismoacoustic monitoring. So this actually unites two of my personal current interests, so I'm really looking forward to the discussion today with our panel of experts here. Just for the avoidance of doubt, we're talking about metrology, which is the science of measurement, and not meteorology, which is the science of weather forecasting. I say that partly with a smile on my face because it's not unusual for the two to be mixed up. So hopefully we're all clear by now anyway with the talks we've had so far. So let's move on with some introductions. We've already heard from Dr. Usuda. So if I may, I'll pass directly on to our other panel members, beginning with Dr. Lind G, who's recently retired from the US Geological Survey. Dr. G, would you like to introduce?
Thank you, Dr. Barnum, and thank you, Dr. Usuda, for a very interesting presentation. And my thanks to the organizing committee for inviting me to this panel. As Dr. Barnum said, I'm recently retired from the US Geological Survey. For 9 years, I was the scientist in charge at the Albuquerque Seismological Laboratory and worked closely with the IMS on station operation issues, including calibration. For the last 8 years, I was the leader of the earthquake monitoring project in the USGS and very focused on the build-out of the seismic infrastructure necessary to support earthquake early warning in the states of California, Oregon, and Washington. And I have to point out, because I am retired, the views I express are my own and not those of the USGS. At the ASL, I oversaw the USGS portion of the Global Seismographic Network, known as the GSN. The GSN has had some first-hand experience with the importance of metrology. It is a network of about 150 high-quality stations distributed worldwide and jointly operated by the National Science Foundation, the USGS, and IRIS, which is a university consortium now known as SAGE. Many GSN stations are auxiliary stations of the IMS. In 2006, researchers identified progressive changes in the long period corner of several stations operating STS-1 seismometers by comparing earthquakes with synthetic seismograms. The ASL instrument testing facility performed a series of experiments and determined that the response degradation was due to corroded components within the feedback electronics boxes, and that the level of corrosion correlated with humidity levels at the station, producing a variable loss in the gain and the long period corner frequency. This discovery brought home the importance of regular and routine calibration to ensure the frequency response of the seismometers is well determined. The GSN as a whole then began to focus on other aspects of data and metadata quality. In one example, the ASL developed a procedure to verify seismometer mid-band sensitivity, orientation, and location on site without disturbing the installed sensors that is now standard practice in all site visits. As part of this practice, field engineers deploy reference kits which contain a seismometer, a digitizer, a fiber optic gyroscope, and GPS equipment. The reference instruments are installed close to the permanent sensors and oriented using the fiber optic gyroscope. After several hours of data collection, one can determine the relative orientation of the station sensors and the mid-band sensitivity using the secondary microseism band in 4 to 8 seconds. This technique has recently been extended to utilize a precise gravity measurement at the ASL to determine an absolute calibration of the accelerometers, which then can be used to relatively calibrate velocity sensors. These developments over the last few years, as well as other efforts to monitor and improve data quality, have had a valuable impact on GSN operations. While there is more work to be done, important steps are underway. Thank you.
Thank you very much. So next we turn to Dr. Svetlana Nikolova. Dr. Nikolova's had several posts, including some time here at the CTBTO, and is currently with Geoscience Australia. So would you like to say a few words?
Yeah. Hello, my name is Svetlana Nikolova. I am currently a seismologist in Geoscience Australia. I'm station operator and NDC user in Geoscience Australia, in nuclear monitoring section. I have worked in PTS in CTBTO for 9 years, 7 of them as unit head of monitoring facilities operation, the unit that was responsible for implementation of calibration of IMS network since 2011. I'll make a and finally, I was many years working in Geophysical Institute of Bulgarian Academy of Science, and later on, which is National Institute of Geophysics, Geography, and Geodesy, and was leading the NDC in Bulgaria, and participated as a delegate at the Working Group B from Bulgaria until I relocated to Australia. I'll make a short summary of the calibration history in IMS because everything went in front of my eyes. We started in 2009 with the calibration project with the aim to start with a few stations to check what is the technical status and to operationalize the command control messages and protocol with the station operators. In 2009-2010, this was more or less done, and we moved to the calibration of first calibration of the primary seismic network. In 2012, we started with the calibration of the whole seismic network. Prior to that, in 2011, we approached all large station operators like GNS, USGS, IDA, DAZE, in order to synchronize and to explain these station operators the sense of the command control and to provide them insights how they have to report the results of the calibration. Thanks to these efforts, preparation of this whole project, the implementation of the calibration in the seismic network more or less went smoothly. And we were encouraged and continued with the calibration of hydroacoustic T-phase stations. And then, when I already left, I believe that we made the first calibration of the infrasound network. For great surprise, it looks that the infrasound network makes the biggest progress in this effort. Well, now I'm going to talk a little bit like a station operator and NDC user with regard to the challenges of the station operator and the NDC user with regard to the calibration. You know that every year there's a report on the calibration which is produced by and presented to the Working Group B, which identifies the problems that are found during the calibration of the seismic stations, infrasound station, or T-phase station. We're suffering with one of the most systematic problems, which is calibration of a sensor with UV orientation, horizontal component. And we still cannot present a meaningful result, and we don't know how to do it. I mean, this is a common problem for all sensors that are having this sort of orientation. And in our specific environment, we have some obsolete software that needs to be replaced. So these are common problems that we're facing as a station operator over the whole network. Finally, I would like to mention a few things which are probably very interesting today that have been presented by in several posters that probably we have to take into account for the future work of the calibration project and implementation of the side-by-side sensor. And I believe that these presentations, posters of John Merchant and Nick Ackerley, point very interesting things which we have to take into account in the future. And lastly, as an NDC user, I would like to mention that we have a real problem with the transformation of the IDC parameters of the station into a different formats, so-called station FDSN XML files. CSS format is a little bit legacy format, and it does not contain so much information that is required now for the FDSN files. I think that this needs to be addressed consistently by the PTS in order to allow this information to be propagated correctly into different softwares that people are using. Otherwise, we're suffering with the variety of small varieties in the amplitudes of the measurements of the same period, on the same time, which are really compromising the trustability of the data. And if we don't have this last stage of the utilizing of the station data into the processing, we are making, it's a big flow in for us in future. Thank you.
Thank you very much. Some interesting perspectives there. Thank you. So next then we come to Dr. Frank Larsonnier. He's from the CEA in France, and I'm sure you've all realized that the CEA are very big supporters of the CTBT from the number of presentations and posters they bring to these conferences. Frank.
Thank you, Mr. Chairman. First, I would like to thank CTBTO to invite me to this panel discussion on metrology. So, to begin, just a brief introduction of myself. So, I'm in charge of quality and metrology for geoscience at CA, and especially in the environmental assessment and monitoring department, which is called DAYS. I joined CA in 2009 now, yes, to work on the improvement of metrology, of measuring change in the infrasound and seismic field, both for sensor calibration in laboratory and also on field. At the same time, I introduced, tried to develop the quality system management based on the standard ISO 17025 standard, which is dedicated for laboratory in the metrology field, and to apply this standard to seismic and infrasound calibration. So in this context, I discovered the specific needs linked to the conformity assessment of the measurement system linked with installed IMS stations, specification which are involved, and the metrological challenges ahead based on standards, sometimes lack of standards, need to develop new instrumentation, ensure traceability to SI unit, and so on. So prior to arrive at CA, I worked 15 years in the French National Metrology Institute, which is LNE. And during these 15 years, I worked on precision engineering dedicated to metrology. I work on R&D in metrology, and specifically in a new field at this time in the mid of the 90s, which was calling at the moment nanometrology, which the issue was to be able to make calibration at the nanometric scale and to develop standards and to put these standards in the industry, and in particular in the industry of microelectronics and nanotechnology. So I learned a lot doing some R&D project with industrial in this field, and at the same time I participate to standards, technical committees, and European project in that field of nanotechnology.
Thank you very much, Frank. So you have several perspectives on this work, from metrology, station operators, laboratory skills, and so on. So I think you've got a very broad perspective on everything we're trying to do here. Okay, so finally then we come to Dr. Thomas Bruns from the PTB in Germany. So Thomas, would you like to introduce yourself and perhaps tell us a little bit about what PTB is and does? Thank you.
Yeah, thank you. Of course, I would like to do that. Yeah, I'm from PTB, and PTB is actually one of those NMIs, National Metrology Institutes, that Takashi introduced in his presentation. So we are taking care for Germany in the first place, and for several other countries in some aspects of the SI units. And specifically me, I'm with my team taking care of acceleration unit or velocity in terms of vibration as well. There's also shock involved. We do also shock calibrations, but yeah, that's not the topic of today, I think. I studied physics in Göttingen in Germany. I have a diploma in the area of particle physics, so high energy quantum thingy things. After that, I made a PhD in biomechanical modeling, FEM models, in the dental medicine department, so quite different from particle physics, but I didn't want to start my productive career in a nuclear power plant or somewhere in that vicinity, so I changed my career track. And towards the end of the PhD, I entered, now 25 years ago, this National Metrology Institute, the PTB, because there was actually a project on dental implants. and finite elements, so that somehow fitted my profile at the time. Anyway, I started at PTB with dynamic force and torque, so mechanical quantities which are usually calibrated only in a static fashion, and the idea was that static calibration is not sufficient for dynamic applications like crash testing at that time. And that started my work in the area of acceleration, because if you look at dynamic forces, this is nothing else than a mass, some kind of mass and acceleration that you have to measure accurately. With this, about 18 years ago, I entered into the area of vibration measurements in terms of acceleration. And this is what we usually do in my labs. We calibrate accelerometer on an industrial scale or for industrial purposes, more or less. And since, well, it depends what you look at. Since 2017, I got in touch with CTBTO because I'm also a member of this CC AUV that Takashi introduced. So I was there when the CTBTO asked for support in bridging the gap between the SI and the stations of the IMS. So there I got more in contact with the CTBTO work. And then about 3 years ago, we started to work on this project I'm currently coordinating. You see on the slide the logo of the Infra AUV project, where we currently try actually to productively bridge this gap and to link the IMS and maybe other geoscience measuring stations to the international system of units. And I think we will probably hear more about it during this panel, and tomorrow and the day after tomorrow in the workshop that we have here.
Perfect, thank you very much. So we've met all of the panel members now, so I think it's time to dig into some searching questions. So Dr. Lassogne, I'd like to start with you first, please. So you and your colleagues at the CEA have been very influential and very active in developing infrasound technology. Could you describe some of the recent developments, both from the CEA perspective, but also from an IMS perspective as well, please?
Frank, that's your turn.
Frank.
Yes,
yeah.
sorry. I was thinking about some.
The acoustics is quite...
Yes, the acoustic is not very good, sorry. So what has been done is in the infrasound metrology field. If you remember the last slide from the presentation of Dr. Takashi, it was very interesting. You saw some picture with some developments. These developments belongs to National Metrology Institute. They belongs to institute like CEA, and we can say that during this last 10 years, 15 years, major development were based on, I can say, the development of complete or unbroken chain for calibration in the infrasound domain. This is very important. If you remember all this metrological organization from the SI unit on the top up to the producer, people who manufacture a system or manufacture sensor, for example, you have a change to make possible and existing. In the infrasound domains, the situation was several years ago, capabilities for calibration of infrasound system at high frequency, I can say high frequency is a few hertz, because some National Metrology Institute were able to calibrate microphones, and microphone could be a very interesting transfer candidate for transfer standards. And after, there were missing calibration capabilities, and after, at very low frequency, at the end, we go back in the static pressure domains in which national laboratory could make some calibration. So in these two parts, there were missing traceability change. So, so the major development appear in that field. With infra AUV, this project was very interesting because it involves several national metrology institutes who developed some primary calibration methods, what are very important because they are the beginning of the calibration process. We participate with the support of the CTBT in the past years with a metrology group that was created by CTBTO. CA participated, but other institutes like Sandia National Labs, NCPA, and different people participate to this metrology group. And in this metrology group, it was a place where we could think about the challenges, how to build this change. We work on very basic things. As you know, in metrology, we are vocabulary is very important. So we wanted to be very clear each other about vocabulary, about what is calibration, speaking in the infrasound field, how to define quantities, what is the measurand. In metrology, we speak about measurand. It was very important to start with this very basic point of view. And so we worked several years. Based to this group, we participate to pilot studies. Pilot study was very important places where we could improve our knowledge, improve the development of the instrumentation. And all of this, in this group, we could introduce the French National Metrology Institute, LNE. We could introduce Richard as SNE, which give us support, very important support from the top of view, from the metrological point of view. And so we can say that in last year, we finished this first part of collaboration with all these people with a comparison, inter-laboratory comparison, respecting all the rules from the comparison. You will see the result of this comparison tomorrow or after tomorrow. It was pilot by the French National Metrology Institute. So all this work contributes to improve the traceability change from the primary parts up to the secondary, because in our institute at CNE, for example, CA, we use some calibrated microphone. These calibrated microphones are calibrated through these primary fields, and after we can use this system to produce calibration on field using a calibration microphone or deploying our calibrated microbarometers. So for me, the main things that we have to see is that we work a lot, several institutes, all on this traceability change to make it possible and existing.
Yeah, thank you. Very, very clear. Okay, so we've heard a little now about this project called Infra AUV. It's been mentioned a few times. So, Dr. Bruns, could you tell us a little bit more about some of the highlights from that project?
Yeah, well, this is, of course, my personal perspective. And for other participants of the project, the highlights may be different. Well, you might expect that the highlight is something to do with the instrument or with the calibration challenges or achievements that we had. But actually, my personal highlight was the meeting of these two communities, because we have in this project station operators like Franck here or his team, or the BGR from Germany operating our stations, and the metrologists from the far other end. And the interesting thing for me as a metrologist was to see that this group of seismologists, for me, I'm the vibration guide, not the acoustician. For me, this group of seismologists, they had a lot of technology and things in place that are among the metrology community are kind of hyped currently. These is things like networked sensors or standardized data formats. I mean, you have your standards for measurement data as well as for the station. I mean, you are not satisfied with the station XML. I would be very, very happy to have something like that in our groups. So it was like IoT, big data, standardized interfaces and things. That was all in place, and apparently these guys had it for years or decades. So that was kind of, frustrating, maybe you could say. But on the other hand, what they did not have was traceability to the SI, absolute calibration, standards for their calibration. So apparently they were still looking for the methods how to do it right, and they didn't know that there were ISO documentary standards already on the stage, available since the turn of the century. So that was actually an optimum situation for a merger. So it was an optimum situation to learn from each other and to generate something really beneficial. And that's what we are currently doing in the project. The project is running for almost 3 years now. We have until the end of this year to accomplish what we promised, and I think we are on a good route. And now for the productive highlights, I think we are in all areas, even including hydroacoustics, we are a large step forward. We are almost finished with the calibration chain. We have the primary calibration in place, still to be validated by comparisons. And we have, even for seismometers now, the on-site calibration under investigation with good results so far. It was already presented at the operators and maintenance workshop of the CTBTO. And I think we are on a very good way. And well, we have to see what the next steps are. I know that NMIJ is also very active. I mean, our project is a European one, so it's not easy or almost impossible to include other NMIs directly beyond Europe. But I think there will be a transnational or transcontinental development in the near future.
So Dr. Asuda, then, would you like to say something about what the capabilities at NMIJ are in this area, in seismic calibrations?
Yes, under the collaboration with other our counterparts, NMIs, and also the national organizations, we are expanding our measurement capabilities, not only from the demands of from the industries, but also from the scientific areas or international activities for those could be contributed to the harmonization of the measurement or technical activities. So we are collaborating each other and looking forward to further collaboration with other parties. Thank you.
That's certainly becoming a theme for this conference, I think, the working together aspect. Okay, Dr. G, I'd like to ask you a question next. So we've heard from Frank about some developments in infrasound technology and how that's being implemented in the IMS. And we hear about the emerging capabilities in seismic calibration and so on. So better understanding of measurement uncertainty and wider acceptance of data and this kind of thing. What do you think the impact can be then from adopting some of these things in seismic work?
There's certainly a lot of opportunities here, and it's been very exciting to learn about what capabilities exist outside of the seismological community. I'll start with the common performance standards, because that's an area in which I am a strong believer of the importance of that. And there have been steps within the seismological community in the past. In 1989 and 2005, there were workshops to develop a consensus on how instruments should be tested and development of minimum specifications. And that's something the USGS has taken advantage of over the last few years in order to establish a minimum baseline for equipment to be used in the USGS and cooperative networks. I think there's opportunity for continuing to develop these standards and measurement techniques. And in particular, I think there's an opportunity to work closely with the manufacturers to add new capabilities that will facilitate the operation of the networks. That's an area that I think we will all benefit from contributing to. The instrument testing and calibration that I described in my introduction is not yet a standard practice in all seismic networks. To make these ties for the traceability, I think, will be a very valuable addition to these on-site calibration methods. I think that will be a huge benefit. I think one of the examples of impact that comes home to me in my recent work is on those applications that rely on a small number of stations. And I'll use the example of earthquake early warning, which in the shake alert system in the west coast of the United States, an alert is declared with just 4 stations. If an instrument response is incorrect, the instrument does not calibrate it correctly, that could result in an erroneous alert affecting millions of people. So it has a very important impact.
Thank you very much. Yeah. It's certainly very critical applications where you need the sensors to just work. Okay, so finally, Dr. Nikolova, I think you can probably provide us with a very good, clear operational perspective on some of these matters. So first of all, could you tell us how on-site calibration is currently carried out for seismic sensors? But also perhaps you could comment on the technique that's now been evolved for infrasound sensors, where you have a reference sensor co-located with a live sensor. Could you comment on those 2 aspects, please?
Yeah. Thank you, Dr. Barham. IMS seismic network is a little bit different in sense of having a lot of stations which are coming from already established networks. So there are a lot of stations which are not the same way designed like an IMS station on the infrasound side. So from that perspective, we have a lot of legacy equipment which currently sometimes fail to be calibrated. It has problems with the calibration. Here we will benefit from the standardizing, for example, the interface between the sensors and the digitizers in future. So this is one of the lessons learned that we had taken from the calibration, electrical calibration of the IMS network. Sometimes we're missing this thing, and we realize after purchasing of the equipment that this interface does not fit. From the perspective of implementing the methods that are now currently used in the infrasound part of the SHI network, we will face most probably a problem on some of the they're not legacy stations, but stations that have been established before the start of the IMS. They're missing sufficient space for the installation of additional sensors. So there's practically no place where you can put this additional sensor in order to make the comparison. With this regard, we are thinking that we have to make any possible use of if there is any other station nearby to that site, for example, from the parent network, in order to use this information and to eventually to use a calibrated sensor that is going to the parent network and to try to use this information. Of course, this will be a work in progress. We have to make as much as possible efforts in order to start really looking into different ways of how we are going to make this comparison, intercomparison between these different sensors, and to establish a standardized way of comparing and software to make be available to the station operators to do this work. And also the community should communicate in this, on this topic and to select the most relevant and most good software. In this regard, I would like to propose that probably it is good to have some sort of collaborative space for the people who are involved in this activity, station operators, NDCs, metrological community, colleagues who are interested in this thing. So I would suggest to the PTS to consider this possibility and to provide this collaborative space in order for future to have this exchange of opinions and to think about future. And lastly, I would like to make one point that we have to make sure that station operators who get involved in this activity report and explain us the difficulties that they have. And one very important thing, now IMS is making the plans for the sustainment for the future. And eventually these needs that are necessary for the installation of this additional sensor has to be assessed and eventually to be put as additional in the plans for the sustainment of the IMS. I think that this will be some sort of proposal to the sustainment plant eventually in future. I think that this will be something useful. And from the perspective of our experience in the implementation of the calibration, I would think that the phase-in approach, including slowly more station operators in these activities, would be the right thing, because this helps us very much to succeed with the calibration. Because if we went like with the whole calibration of the network at once, wouldn't be all these things. Is very well. It's very necessary to be assessed and later on implemented on the next stage. So little by little, step by step, but in 12 years we managed to calibrate the whole network. So basically, yeah, so from 13 years. The start of the project was 2009, now it is 2000. So in 13 years we managed to do this whole thing, all stations, and practically for nothing. Well, thank you.
Yeah, thank you very much. So that's a very interesting proposal to come up with some kind of discussion forum or a means of communicating and going with a two-way flow of information between the station operators and the calibration community and so on to have a kind of knowledge transfer process to take place. Okay, time is running on. I think it's probably time to turn to you in the audience now and ask if anyone has any specific questions for members of the panel. Please feel free to come up to the microphone. John, yeah.
Yes, thank you for the interesting introduction and the comments on metrology. As someone who has a lot of interest, especially in traceability, metrology, and calibration, I understand the needs and the benefits from the perspective of a laboratory to have these, but quite often in the IMS, we're in the situation where the monitoring network, the stations, the sensors are deployed and operational for decades at a time with no opportunity to retrieve them, to move them. I was wondering perhaps if any comments on, from a metrology perspective, how you deal with those types of challenges where you're now reliant on a diverse community of station operators to help to ensure the continued traceability of the monitoring system.
Yep. Does anyone have any comment? Yeah, Thomas.
Yeah, maybe I can answer. Not so much from the direct practical point of view, but from the concept that we follow. I think in infrasound it's already well known and actually already implemented in software, in the CalX-Pi software that also had a stage here during the conference. The idea is to do the on-site calibration based on, well, probably in most of the time, using natural sources of excitation. Of course, you cannot apply a shaker to a station or to a vault or a borehole seismometer, but nevertheless, you could have a transfer standard, as we call it, a transportable reference seismometer, for example, that you have calibrated in the laboratory under best conditions with lowest uncertainty, and then you move that into the station side by side with a seismometer in the vault, and then do what is usually called the Gabrielsen method. So do cross-correlation analysis basically to find the common signals and use them for calibration of the full frequency range of the sensor. The same as I said, is already done with some success in the infrasound area, and we are currently investigating that for the seismometers. Actually, my hope is that we are a little bit in a better situation for seismometers, because my hope is that a seismic station is moved like a solid body, a rigid body, you would call it, so that you cannot only calibrate the seismometer that is standing next to the one that you transferred from the lab, but you may be able to calibrate a whole area of your station against that reference. So I don't think we invented any concepts here, but we transferred them. We have so far good results. And we are working on it. We have to evaluate it still, of course, but there are concepts available.
Yes, I can add a few words for infrasound point of view. For said Thomas, for infra AUV, now we are able to put on field standards and to be able to, with portable system, small calibration benches, can make some calibration with traceability, because we use a standard that is calibrated, so we can calibrate microbarometers on field, and the microbarometer that is used as reference microbarometer in the Gabrielsen methods. So we push metrology on field. We did it. And it can be done periodically.
Okay. Are there any other questions? Doesn't seem so right away. So maybe I could ask Dr. Osuda once more, please. Do you have any comments on how the BIPM and the CCAUV and even the National Metrology Laboratories can assist in this effort to bring this traceability and the link to the SI out into these field measurements? Can you draw any parallels also with the way it's working currently for the ionizing radiation field?
Yes, the function or the mandate for the BIPM, CC, or NMI is quite simple. Defining the fundamental and derived unit, and ensuring the traceability of measurement. But over the time, the requested functions for BIPM or CCs and NMIs have been changed based on the technology and demands from our customers or social needs. And as I explained in my presentation at the beginning of the metal convention, the masterpiece of the kilogram and the metal were maintained at the international organization, namely BIPM. We could rely on, or we had to rely on that system. But now, a lot of NMIs can realize its own measurement standards. That means we have quite redundant sources for traceability. However, we have to evaluate, or we have to validate those equivalency. So we introduced CIPM MRA. With this regard, you or CTBTO communities or any other communities could contact to each NMI, your surrounding NMI, to realize or ensure your measurement capability for the traceability to the SI. This is one of the current situation. And talking about NMI, our community, based on the high demand from industry or scientific community to achieve more accurate measurement standard, it becomes very costly. For example, PTB in Germany and NMIG in Japan, we can realize the mass standard, kilogram, by the fundamental constant, Avogadro constant. But the facility is very, very costly, and we have to replace the facilities which amount of some million of euros we have to replace periodically. So with this regard, NMI has to communicate or collaborate. This is the current situation. So anyway, the demand for the metrology or measurement, the equivalence of measurement results, now we have high demands from every aspect. And NMIs are collaborating to ensure the international traceability and equivalence of the measurement standard. With this regard, we should communicate each other to identify the needs and future collaboration of each organization.
Okay, yeah, so the NMI community strategy is actually quite clear.
Yeah.
It's well articulated, and there's a good plan in place for addressing that need.
Yes, and like Thomas pointed out, any other topics, not only the quantity itself, but the big data or statistics or computational science should be also introduced to the measurement standards. So with above regards, also we have to communicate and employ other findings and properties. Thank you.
Thank you. Okay, we have just a couple of minutes left. If there are no further questions from the audience, oh, there is one. Yeah, please go ahead.
Yeah, thank you very much, panelists, for giving us a very detailed view of what's possible in these days in terms of calibration. I'm a field seismologist. I mean, you see my outfit. But what do we learn from it? So if you guys can provide us with 1% more better calibration, what do I learn as an operator of a seismic station? What do I learn from it? The seismic station does not only consist of the seismometer. You have the digitizer, you have the volt, you have all the equipment that's surrounding it. And I want to know what goes wrong when you give me another, microvolt per second better calibration. I want to know what caused the problem in the first place. And the question is, can you help us understand these problems, that it's not just the seismometer, that it's a whole group of instruments that you have to run and keep running in order to keep a seismic station running?
Yeah, I'm going to make one quick comment on that before I ask someone in the panel. For me, the big benefit is the linking the measurement with something physically meaningful that's established at the very fundamental level. So your velocity or acceleration that you measure in the field is actually a physically meaningful measurement when you have the traceability in place for that measurement. So it's not just about improving accuracy and so on, it's the fact that you can make a measurement in your station, someone across the world can make a measurement in their station, and those two measurements are the same. They're based on the same physical basis. That's the benefit, I think, of the traceability part, not necessarily improvement in accuracy, although there is an angle. Thomas, I suspect you'd like to say something about measurement uncertainty.
Yeah, I mean that absolutely correct. I think on a different level, it may not change anything in your results as a field seismologist, as you say. But if you look at it from a more formal and jurisdictional point of view, Takashi introduced this CIPM MRA. The CIPM MRA is an international contract, just like the CTBT, which guarantees that the signatory states, which are on the same level like the CTBT number of signatories, that they mutually accept calibration results and the traceability among each other. And I think it's a very generic benefit if you could put the IMS measurements under this umbrella of the SI and its mutual recognition and acceptance of calibration and therefore measurement results. This is a very formal thing. I'm aware that probably there's not very much changing immediately if you gain traceability, but we discussed it before and at the poster session. You often have a sudden and unexpected progress in a technology once you have other means to validate it and to investigate it. And one of the things I think we will have some progress is by this kind of absolute calibration is the relationship between the ground response, as I call it, from the seismometers to the electrical response of the seismometers. And as you say, you have different environments at seismic stations, so how do you investigate the influence on whether your seismometer is placed on concrete floor, on rock, or on, as I learned, on a glass plate with sand on it, or there are all kinds of mounting conditions. You have to understand the influence to improve your situation, and you need to investigate it under controlled conditions, otherwise you cannot understand it. So I think there will be some benefit, although I could not name it immediately now. We will see.
Okay, so I'm conscious of the time. I think we've reached the point where I need to try and wrap up. There's been such diverse conversations this afternoon. It's quite difficult to wrap up, but I'll try and do my best. So we've heard about some of the operational challenges in calibrating, particularly seismic sensors at IMS stations, some of the complexity of the tasks involved, some training issues around station operators, intensive planning requirements, and so on. And actually, these sorts of issues are having an impact on data availability and mission capability of the stations. So I think that's an important finding from probably not new, but something that's come up today. There's also scope for the IMS seismic operations to build on existing practices in other networks and to learn also perhaps from some of the developments in the infrasound technology area and adopt similar approaches going forward. There was also some comments about the benefits of better specified equipment, perhaps overcoming some of the issues with legacy equipment and so on, and compatibility and interoperability of different equipments. And I think the benefits of further collaboration with the metrology community are quite clear. We didn't really touch on ISO type standardization, but I think there could also be a role there that we haven't really discussed properly today, but maybe we could have a look at some of that in the workshops that are happening tomorrow and the next day. And actually, again, we didn't really touch on it, but the infrasound technology all the problems are not fully solved. There's still a lot of issues around on-site calibration and so on, which we still need to work on. And then finally, the wider seismic acoustic communities, for example, in civil applications, are most likely going to benefit from a lot of the developments that are put in place for operating the IMS. So there is an added value for the investment that goes into the IMS through these use of the data and civil applications taking up some of the developments there. So I think we've reached the end. It just remains for me to, first of all, thank all of you members of the audience for showing an interest in this topic and coming to listen to the panel today. Special thanks, of course, to our panel members for sharing their knowledge and their opinions. I hope you all agree that there's been some very interesting topics discussed and probably scope for further discussions both today and into the future. I'd also like to thank the organisers of SnT for featuring this topic and making space for it in a very busy agenda, and for their excellent organisation actually leading up to this conference. It's been a pleasure. They've really made the process of getting this panel in place straightforward and easy. So thank you all, and thank you all for attending today.